Hi, in this video we are going to talk about Sudoku problem. This is a popular puzzle that we generally see in newspapers. We are given a partially filled grid and we need to fill the empty cells. In this example, the empty cells are represented as 0 and the filled cells have these numbers with black color 1, 3, 2, 1. We need to fill the empty cells here and there are certain rules to fill the empty cells. The first rule is every number in every row should be different. For example, if you consider this row, these two numbers should only be filled with 2 and 4 because 1 and 3 are already there. The second rule is every number in every column should also be different. For example, if you see this column, the only allowed numbers are 3 and 4 here because 1 and 2 are already there in this column. The third rule is every item or every number in every subgrid of size 2 cross 2 should also be different. So in this 4 cross 4 grid, we have 4 subgrids of 2 cross 2, this, and this. And all the numbers in every subgrid should be different. So if you see this subgrid, we can clearly guess we need to fill 3 here because 2, 4, 1 are already there in this subgrid. So we need to fill the remaining places following the rules which I just talked about, the 3 rules, every row, every column and every subgrid. Now one thing about this Sudoku problem is the size of given grid is always a square. It's either 4 cross 4 or 9 cross 9 or 25 cross 25 and it's partially filled. Please note that if we have 9 cross 9 grid, then there are 9 subgrids of size 3 cross 3. This is first subgrid, this is second subgrid. These subgrids are highlighted with blue colors, right? So first 3 subgrids, then these 3 subgrids, then these 3 subgrids. Also, the numbers that we are going to fill, that those numbers range also depend upon n. It always goes from 1 to n. If you have 9 cross 9 grid, then the numbers are from 1 to 9. If you have 4 cross 4 grid, then the numbers are 1 to 4. And in 9 cross 9 grid example, numbers in every row should be different, every column should be different, and numbers in every subgrid of size 3 cross 3 should also be different. Now please pause this video and write a program that takes this grid as an input and produces this grid as an output. It should basically modify the same grid and change the zeros to filled numbers. And please note that there can be multiple possible answers. You just need to find one answer of these. And if there is no possible answer, suppose a user gives you an input where it is not possible to fill the empty places following the given rules, then you do not need to produce any answer. You need not to print anything as an output. You can simply return false. Let us talk about solution of this problem. A naive solution is to try all possible configurations for all the empty places. How many configurations can be there in naive solution? Say there are x empty places in your given Sudoku puzzle. Then every place can be filled values from 1 to n. So you are going to have x raised to the power n possible configurations. So in naive solution, we generate all x raised to the power n possible configurations. For every possible configuration, we check whether it is following all the rules or not. If it is following the rule, then we return and print the solution. This is too time-consuming solution. The idea is to use backtracking here. In backtracking solution, what we do is we first find a free cell. For example, if this is our grid, we find a free cell as this cell. Now what we do, we try putting all the numbers in that cell one by one. We begin with number 1. We try putting number 1 here and we check if putting number 1 is safe here or not, like any other backtracking solution. So in safety, we check for 3 things. Do we have 1 in the same row? Do we have 1 in the same column? Do we have 1 in this grid? If we get false in any of these tests, then we do not place 1 and we try the next number. So we find a free cell as this cell. We try putting 1 here. And when we put here 1, we fail in safety test. So we do not put 1. Now we try putting 2 here. 2 we can put. So right, because it passes the safety test. You do not have 2 in this row, you do not have 2 in this column, and there is no 2 in the current cell as of now. So we can put 2. After we put 2, we recur for the remaining empty cells. And in the recursive call, we again find an empty cell and we try putting different numbers. So when we recur, we come here and as we find an empty cell, now in this cell, we try putting all the numbers. We try putting 1, then 2. So if we try putting 1, it fails in the safety test. We try putting 2, that also fails in the safety test because you have 1 and 2 in the same row and same column. 3 also fails because you have 3 in the same row. 4 passes the safety test, so we put 4 here. And then we recursively call solve function for remaining empty cells. So we find the next empty cell as this one. When we find this empty cell, we try putting all the numbers here one by one again. We try putting 1. So 1 cannot be placed here because it fails the safety test. 2 also cannot be placed because 2 is there in the same column. It's there in the same row also. 3 we can place. It's not there in the same row. It's also not there in the same column. And it's not there in the same grid also. So we put 3 here. Once we put 3, we again recur for the remaining empty cells. So we recur for this, right? And when we come here, we again try putting all the numbers. 1, 2, 3, they all fail the safety test. So we put 4 here. When we put 4 here, we recur for the remaining empty cells, right? After putting 4 here, we recur for the remaining empty cells. So we come to this cell. Again, in this empty cell, we try putting all the numbers. So we begin with 1. 1 we cannot put. 2 also we cannot put. 3 we cannot put. 4 also we cannot put because 4 is there in the same grid. So what we do now is we backtrack. We backtrack and go to the parent call. In the parent call, we had put 4, which means we had already tried every number from 1 to 4. So parent call also backtracks, right? When you come into the recursive call of parent, you put 4 here and then you again recur for the remaining cells. So now you come to this cell. Now you again try putting all the numbers and check for their safety. So 1 fails in the safety test, 2 also fails, 3 passes the safety test, so you put 3 here. Now you again recur for next empty cell. Now you come to this cell. And this time you again try everything. 1 fails the safety test, 2 fails the safety test, 3 we can place here, so we place here 3. Now we again recur for next empty cell. This time we come here and we try all numbers from 1 to 4. 1, 2, 3 fail the safety test because you have them in the same row. You can place 4 here. Now we come to this cell. When we try to put different numbers here, we again check for the safety test. 1 passes the safety test. So we place 1 here and we recur for the remaining cells. When we come here, we again try putting all the numbers. We try putting 1 fails the safety test, 2 fails the safety test, 3 passes the safety test, right? So we put 3 here. Now we again recursively call, and this time when we recursively call, there are no empty cells, so we return true. And that's what we are doing in this solution. So it's a simple recursive solution. What does that do initially? It finds an empty cell, right? It traverses through the whole grid of size n cross n, and it checks if it finds an empty cell or not. See, this loop will break if it finds an empty cell. It will not break if there is no empty cell. If it does not break, then I and j, they both will become n, right? You will traverse through the whole cell and your I will n and your j will be n. Then that's when you will stop. So you return true. It means there are no empty cells left, right? So after this part, you come to this code only when there is an empty cell. Otherwise, you would have returned true from here, right? So we execute this part once we find an empty cell. So what we do here, we try putting all the numbers in this empty cell, and before we put that number, we check for safety, right? We call a safe function, and if safety test passes, then we put that number in this particular grid. And after putting this number, we again recursively call for remaining empty cells. So when you recursively call, your execution is again going to begin from here. Then what it's going to do, it's going to try to find an empty cell, and then it's going to come here for remaining empty cells, right? After you have, solved the solution recursively for remaining empty cells, you are done. You need to return true, right? You need to return true. You need to place this number and you return true, right? And if recursive calls do not return true, right, then what you need to do, you need to backtrack. You need to remove this number that you placed. So you remove this number that you placed here. We placed n here, then we recursively check for the remaining empty cells. We did not find a solution, so we backtrack, we remove 0 from here. And then we try the next number, right? So we tried putting this number in, and if it did not work, then we tried the next number. And if none of them work, then we return false. That's the simple idea of this backtracking solution. How does this escape function work? So we are given I, j and n. I is the row number, j is the column number, n is the number to be placed. So we have first loop which checks, do we have number n already there in the current row and current column, right? This is where we are checking for current column, and this is where we are checking for current row. So if we find in the current column and current row, or in the current row, we return false, right? If we find anywhere. If we do not find in the current row and current column, then we check in the current grid. Now, how do I find coordinates of all the elements, all the cells in a grid given a random cell? So the idea is this: every cell, every subgrid of size 2 cross 2 begins this way. See, this grid is 0, 0. It begins with 0, 0. This begins with 0, 2. This begins with 2, 0. And this begins with 2, 2. So you can notice that all these subgrid starting points are multiples of 2, right? So if n is 4, then they are multiples of 2. If n is 9, then they are multiples of 3. You can do it by drawing some grids using pen and paper, right? So they are multiple of 2. So we first find the starting coordinate of the subgrid for the given random coordinate. And we use the same idea here, right? We find the square root of n, and we do I modulo s. S is the square root of n, and j modulo s. S is again square root of n. I and j are row and column indexes which are given to us. So by doing this computation, we find the starting indexes of the subgrid of this particular cell. Once we have found the starting indexes, we just go through this subgrid from I equal to 0 to size of the subgrid. Size is always square root of n, and j equal to 0 to square root of n, which is size. And what we do inside this loop, we go through every cell, I plus starting row number, j plus starting column number, right? And we check, do we have n already placed in any of these cells in the subgrid? If we find n, we return false, right? And if we do not find n in the subgrid, we return true. So this is how our escape function works. It checks in the current column, current row, and then checks in the subgrid. So the reason for using backtracking is again same here. We have one simple recursive solution, generate all configurations, and then check which one of them is valid. Instead of doing that, what we do here, we try placing a number, and if this number can be placed, then we recursively check if we are getting a solution or not. At any point after making a move, we realize that we are not going to get any possible outcome from this move. We do not go down the recursion tree. We simply cut down the recursion tree from that point, and then we try something else. So we cut down lots of recursive calls like other problems, and we solve this problem efficiently using backtracking.